Plant density, an overview. Density is one of the main attributes of vegetation, and it is commonly used to quantify and describe vegetation. Density is defined as the number of individuals per unit area. Sometimes, with certain species, it's difficult to discern what an individual is, and it may take time to identify individuals. And it may not be necessary to identify individuals depending on the management objectives for doing the study. So density can be defined as the number of counting units per unit area. And then, of course, it would be important to clearly define what a counting unit is. We often use density measurements in order to describe the spatial proximity or closeness of individuals to one another. So density relates to the way that individuals occupy space in a landscape. The term density is often used synonymously with abundance, but these have very different meanings, and so it's important to be clear when you're using the term density versus abundance. So we'll take an example where we compare the populations of two states, Arizona and Tennessee. The reason we'll compare these two states is that based on the U.S. Census of 2010, the populations of these two states is very similar. They only differ by about 45,000 people, and Arizona is less than 1%. The population of Arizona is less than 1% larger than the population of Tennessee. Now, the land area of these two states is different. Arizona has over 113,000 square miles, whereas Tennessee is about a third of that, nearly a third of that, at 41,000 square miles. So if we want to describe the populations of these two states, if we discuss them in terms of abundance, they're nearly equal. They have nearly the same number of people per state. But density is in the units of individuals per unit area. So if we describe the density of Arizona in terms of, it is 56.3 people per square mile. The density of Tennessee is 153.9 people per square mile. So Tennessee is nearly 3 times more densely populated than Arizona. What are some of the best uses for density data? Well, certainly whenever counts are appropriate. In demographic studies, where we may be interested in population dynamics, in looking at the age structure of a population, how many developing individuals are there, how many decadent individuals. We're looking at recruitment or mortality. This has direct applications. Density data are often used to study the success or the progress of reseeding and revegetation projects, because we want to quantify seedling recruitment in a timely fashion so that we can make management decisions based on that information. Density data are also used for conservation purposes, or when we're monitoring the populations of rare and invasive species, because we can determine whether the number of individuals or the size of the population is nearing a threshold value. And density data are often used as indicators of population stability, being able to discuss trends and rates of change. So they have direct application to inventory and monitoring. Some of the weaknesses of density data, the primary one is that density does not relate to dominance or importance, because it doesn't clearly reflect resource use. In this schematic, we're looking at a quadrat that has two individuals of a green species. They tend to be quite large individuals and probably use quite a bit of resources, say water and nutrients. And there's also 20 individuals of a very small species. Those are the red individuals. Now the density of the red individuals is 10 times larger than that of the density of the green individuals. But we certainly would say that the green individuals are more dominant in this particular situation. Biomass and cover are the attributes that are better indicators of ecological importance and dominance. Whenever we are preparing to take measurements, we always need to establish our ground rules. And as for all of the measurements that we take using different attributes, it's important to make sure that the decisions we make about ground rules are determined by our management objectives. One of the main ground rules that's important for density is to clearly define the counting unit, and we've already discussed this slightly. For example, the individual in this picture is an ocotillo. That could be our counting unit. Or we may, depending on our management objectives, be more interested in plant parts, such as stems, inflorescences, or even individual flowers. So it's important to define the counting unit based on the purpose for collecting that data. Another important decision to be made and clearly stated is the level of identification. We're often interested in identifying individuals to the species level. This can be time consuming, especially if certain plant characters that are helpful for identifying species, such as inflorescences and fruits, if they're not available. And so depending on what your management objectives are, it may not be necessary to identify a plant to the nearest species, but nearly only to the nearest to the genus. So in this case, instead of identifying the plant as Bouteloua areophyta or black grama, it may only be necessary to identify that it is a grama grass. Again, we may not even need to identify plants to the nearest species or nearest genus, but simply to be able to say, oh, that's a perennial grass. So identifying the plant to the functional group may be all that's needed. There are other ground rules that apply that are specific to the different methods that are used. So how do we measure density? Well, there are three main approaches to measuring density: abundance classes, counting methods, and distance methods. The abundance class method is a visual rating system, and this is very good for large-scale surveys because it's rapid. It can be done relatively quickly. With the abundance class approach, we use estimates that are in a range of scarcity to plenty. And so you would go to an area, and depending on which classification system we're using, you would identify the different species that are there and then say whether they are rare, very rare, occasional, abundant, or very abundant. And there are other classification systems that just use different terms, such as the one on the right that compares how sparse plants are compared to how numerous they are. Now, this kind of data is qualitative data. That's one of the disadvantages of it. And also, it can be difficult to ensure consistency either between different observers in the same location, or consistency even within an observer if they are quantifying abundance in different types of vegetation. The next main approach are the counting methods. Now, these are plot-based methods. The first kind of plot that we consider are quadrats or frames. These can be any different sizes and shapes. The most common shapes are square, rectangular, or circular, and different sizes based on the needs of the study. Frames are generally have edges, and they're hard, and you have to carry them. So if you need a frame that is quite large, it can be difficult to carry them around in the field. And so then we may instead use plots that don't have edges. These are usually established using transect tapes, and then usually you can stake the corners and sometimes leave the tapes in place to have a temporary edge to your plot. They can be variable sizes and also shapes. And when we're measuring density, sometimes if we want our plot to be very long and relatively narrow, we have a special term for those. We call those belt transects. When we're selecting our quadrat or our plot size and shape, those decisions are based on the size of plants and dispersion of plants. So we could go from a small quadrat to a larger quadrat that may be more inclusive, to an even larger quadrat that may include both small and large individuals, and also cut across clumps. The shape that we use for our quadrats also has an influence on our density measurements. So rather than using a square quadrat, we could use the same size, but then make it rectangular, or make it even longer and narrower. In this case, generally as the quadrats get more rectangular and more elongated, they tend to cut across clumps, and so in scattered, sparse vegetation, it's a good choice. Now you may wonder, well, what if I'm interested in plants, in multiple plants that have different sizes and that are distributed differently in the landscape? In the case of diverse life forms, we will use nested quadrats, where we use different size quadrats that are measured simultaneously. So the placement of a nested quadrat, we do multiple measurements inside these multi-sized quadrats. Whenever we're using quadrats or plots, there's always the potential for errors at the boundaries because of edge effects. And that leads us to our last major category of methods, which are the distance methods. Distance methods are plotless. This eliminates edge effects and the need to make decisions at boundaries. Using distance methods, we measure the distance between plants, and it's most commonly applied in forested systems, in woodlands, and in some shrublands, oftentimes when we're only focusing on one or two species, and they can be closely spaced or spaced at distance. The unifying concept is the concept of mean area. Mean area is inversely related to density. The units of mean area are the average area per plant, and that is the inverse of the units of density, which is the number of plants per area. So it's very easy to convert from mean area to density. The main approaches that are used for distance methods are nearest individuals, nearest neighbor, random pairs, the point center quarter method, and wandering quarter. More information about using counting methods and distance methods will be provided in subsequent lessons.